The ideal vapor compression cycle assumes that we are using a pure refrigerant, such as ammonia. Unfortunately, in the real world, non-condensable gases can find their way into a system. A non-condensable gas is an undesired foreign gas in a refrigeration system. It travels through the cycle with the refrigerant, but it does not assist the refrigerant process in any way. Since the gas takes up space that would otherwise be occupied by the refrigerant, non-condensable gases decrease a system's performance. Non-condensable gases are mainly introduced in two ways. First, when performing maintenance, equipment is open to atmospheric conditions. If the equipment is not evacuated before placing it back into service, the air in the equipment will become trapped in the system as a non-condensable gas. Second, systems that require low temperatures operate at vacuum pressures. This means that if there is a leak, rather than refrigerant leaving the system, air will be sucked into it. Non-condensable gases hurt a refrigeration system in a variety of ways. Electricity use will increase since the compressor must compress the refrigerant and non-condensable gas. Due to the increased total pressure in the system, the theoretical discharge temperature at the compressor outlet will be higher. This will increase wear and tear on the machine and break down the oil more quickly. Sometimes, the water vapor in the air can react with the refrigerant to form acids that are harmful to the system.
It's really important to deal with non-condensable gases because they can wreak havoc on a system in a variety of ways. First of all, we know from Dalton's law that the total pressure is just the sum of the partial pressures. So if we add 10 psi of non-condensable gases, that's just going to increase our discharge pressure. Therefore, the compressor is just going to have to work that much harder. Compressor working harder equals more kilowatt hours. That's going to equal more money spent on your electric bill, which is a net negative. Furthermore, it's going to increase the compression ratio. That's the ratio of the discharge to the suction pressure. And we know that as the compression ratio increases, so does the theoretical discharge temperature. And that will cause wear and tear on other components, because more temperature equals more heat, which equals more friction, which will equal quicker equipment failures. So for all those reasons, it's really important to deal with non-condensable gases.
It is important that systems be checked for non-condensable gases periodically. When discovered, non-condensable gases must be removed or purged from the system. There are three primary methods of purging non-condensable gases. Manual purging involves the deliberate release of trapped gases, such as air, that accumulate in high-pressure areas like condensers and high-pressure receivers. Manual purging is performed by an operator using an isolation valve installed at a suitable purge point. Refrigerated purging improves on manual purging by cooling a small sample of the refrigerant gas mixture, often called foul gas, so that the refrigerant can be condensed and reclaimed, while the non-condensable gases, which do not condense, are separated and vented safely from the system. Automatic purging refers to the continuous or periodic removal of non-condensable gases from the system using an automated purger device. Unlike manual purging, an automatic purger operates without constant human intervention.